Thanks, Amma, for introduction. My name is Michio Honda, and I'm presenting a PASTE, which stands for Packet Store. So before going to the main topic of this talk, let's quickly review memory hierarchy we know today and that we will see tomorrow. So we can access data on CPU cache or main memory relatively quickly, just using load store CPU instructions. But their contents go away when your machine reboots, and their capacity is relatively limited. So underneath, we have secondary storage, which is hard disk drive or SSDs, and their contents are by reboots. And however, the access data there is much slower than doing so to DRAM or CPU cache. We also have to issue system call to access data there. But we will have slightly different memory hierarchy tomorrow. So we will have non-volatile main memory, which is also known as persistent memory or storage class memory. There are two important characteristics here. So first one is accessing data there is almost as fast as accessing data into the DRAM. Maybe slightly slower, but still 2 or 3 orders of magnitude faster than the disks or SSDs. The second important point is now we can access persistent data just using load and store CPU instructions. We don't need we don't need system call anymore. So let's take a look at how this memory hierarchy affects end-to-end data transfer over the networks. Imagine that a client sends 1.2 kilobytes of data over the network, and client expects the server reliably store this data in its the stable storage. So just over using standard TCP/IP and HTTP. So in the world of disks or SSD, there is nothing to do with networking, because the networking part only takes 23 microseconds for one trip, even including TCP and HTTP. But directly writing data to SSD or disks, it takes 1.3 milliseconds. Okay. But this situation completely changes if we have NVMM or non-volatile main memory. So now the persisting data only takes 2 microseconds. Not only because of faster storage media, but also new access method. We don't need system call anymore. We can just memory copy data to NVMM. So now the networking dominates end-to-end latency. So you may think that given that the persisting data only costs 2 microseconds now, maybe it comes almost for free. And we can just improve some network stack as the client or the server. But unfortunately, this is not true. So usually, the server handles a lot of concurrent client requests, say using concurrent TCP connections. So to process a lot of client, server usually runs the code something like this. It fetches a lot of events or file descriptor at once, then process each of them one by one. Okay, so which means there is a multiple of cost of persisting data in a single event processing cycle, which delays subsequent event processing a lot. So here is the end result. So white bar or boxes indicate throughput and latency of not persisting data at all. So we don't have the line of orange one. We don't have the orange line. So on the left is throughput and right is latency. But when we do persist data, so we see almost half of the throughput, and we also increase latencies in proportion to the number of concurrent connections or concurrent requests. So in the last half decade, we have seen a lot of innovations at storage and network stacks. But the cost we have shown before is actually the cost of moving data from network stack to the storage stacks. So we can't solve this problem as long as we consider these stacks in isolation. So addressing this cost is precisely the goal of PASTE by bridging a gap. So here is the design goals of paste. So we really want to avoid data copy, even for persistence. So we instrument the NIC to DMA directly to NVMM, not to DRAM. Okay? But on the other hand, we also provide selective persistence. So persisting data on NVMM is indeed cheap, but not comes for free. So we want to avoid persisting unnecessary data. For example, imagine some kind of key value store. So in addition to write request, you also get a lot of read requests. You don't have to persist such a read request, right? So to achieve this selective persistence, we simply exploit natural effect of modern NICs DMA, which happens physically on last level cache, last level CPU cache, while it logically happens to main memory. So next, we also would like to help application organize their persistent data structures, which means some data structure that can be recovered after a reboot. So to this end, we provide index named packet buffers backed by a file. So we also want to offer generality and safety as well, because we believe NVMM will be ubiquitous rather than being just exotic storage device. So for that reason, we support standard TCP/IP even in the kernel, and we also use a NetMap API for efficiency and safety. So using these primitives, we can offer applications the same safety which application benefit from Socket API today. So also we also take all the best practices from the modern network stacks, such as run-to completion, blocking, or busy polling, or batching. So now let's try to understand how paste works in action. So first of all, we have to create a file on NVMM. Okay? We can do this in a way something similar to the creating RAMFS today. So in this case, we created the file system on NVMM under /bound/pm. And we created some shared memory region backed by a file under /bound pm and pp. So there is some important data structure. The first one is pbus. Pbus are fixed size packet buffers, also indexed. And there is also structure called p-ring, which is a kind of abstraction of the pbus, which contains a slot, each of which points to pbus, or it's just the index of pbus. So pbus stands for the persistent buffer. So the next, imagine that. So then how to start receiving packet. Okay. So application first call poll system call. Okay. Then it kicks NICs packet IO and has the TCP/IP implementation process each of these packets. And just imagine that we got 6 in-order TCP segments. So these are indicated by yellow. Sorry, we have 7, but actually we have 6. And since they are in-order TCP segments and ready to be consumed by application, so these pbus are set to p-ring. So now we have a p-ring which has pbus 0 to 6. And the kernel also advanced tail pointer to indicate that application can consume the data from 0 to 6, or from car to tail. So at this point, the application returns from poll system call and then start reading the pbus. Again, we don't have to copy data at all to read the data here. So imagine that application identifies that the pbus1 to be persisted. Okay? So remember that the NIC DMA happened to last level CPU cache, so the application has to explicitly flash the data on pbus to actual main memory from CPU cache. So we can do that just using CLFlash or CLFlash of CPU instruction. This is not system call, so this is not as expensive as system calls. So the next step application needs is now application has to memorize records the metadata of this pbuf. Okay? So the application simply writes down some index of pbuf and some data offset and length. So remember that pbuf is already persistent data representation because we already know the base address because this entire people is just a file on NVMM. So just by knowing this file name and buffer index and offset and length, we can precisely recover the data, this data even after reboot. So the next step is the applications has to prevent the kernel from recycling this persisted buffer. Okay? So what the application do is application simply moves pbuf1 out of the p-ring and instead they fills another free pbufs, in this case it's 8, to the slot 1. Okay? So in this way, the application can avoid the pbuf1 is recycled by the kernel when returning this slot to the kernel. So just imagine that some same procedure happened to the pbuf2 and 6. And finally, the application advances car pointers, which indicated the beginning of the new data, to the tail to indicate the kernel that application finished or consumed all the data. And these pbufs pointed by returned slots are recycled by the kernel eventually. So so far the P log represented the write ahead log. This is just simply serially appended data structure, and appended data structure, which is often quite commonly used for databases to speed up transactions. But of course, we can create the much more complicated data structure, such as B+3, because our primitive is pretty simple, just data buffer index, offset, and length. So now we are going to evaluate the paste, and we show we answer 3 questions in turn. So first of all, how paste outperform existing systems? So in this setup, we simply test write-ahead logging, so simplest data structure to be persisted. Okay? And we test 2 data size cases, one is 64 byte and one is 1.2 kilobyte. So we compare against normal Linux and StackMap, which is the current state-of-the-art network stack, but it has to copy data from DRAM to NVMM. So for small data cases, we don't see that much improvement, but this is kind of expected because the cost of copying data is anyway small. So when we start using large data, we can see a lot of improvement over Linux and StackMap. But the next question is, what if we use a more complex data structure rather than this simple one? Do we still have benefit? So this is the case with B+3. In this case, client generates just write request with random keys, whose key space is 1 million. So we can still get a lot of performance improvement, and one of the most interesting, but overall throughput is lower than the write-ahead logging case. This is because there is some tree traversal operation of overhead. So one interesting thing is even for small data, we see improvement over StackMap. This is because B+3 is much more memory intensive. So just saving a little bit of data copy cost contributes performance a lot. So the next question is paste applicable to existing applications? So we ported some Redis, popular persistent key value store, to use paste. And we compare against normal Redis, which run on Linux, and also normal Redis, but which doesn't persist the write request. Then we run paste, which always persists the write request. Okay? So we test using the different data sizes, also the different write request ratio, also changing some patterns of distribution between the uniform one and the skewed one. And these two workloads correspond to popular YCSP workload, which corresponds to read-heavy and read-mostly and update-heavy workload. So as expected, so we see larger improvement when we have large data and when we have higher write request ratio. So one interesting point here is having fast NVMM and the paste, we can outperform even the Redis which doesn't persist the write request, which means we can get persistent for more than 3. So the final question is paste useful for systems other than database or file storage? So we often see some software packet forwarding systems that has to log or store a packet before forwarding these packets. So we can see such a system in fault-tolerant middle box and also some traffic recording or capturing systems. So to implement packet logging feature, we extended M-switch, so which is a very scalable software switch that can serve some hundreds or thousands of the network functions on top of it. So we compared performance of the packet logging with M-switch and using without data copy or using paste. And we compared it against a version which copies data to persist to record packets. So for all the packet sizes, we see quite nice performance improvement. So here's the conclusion, like in short, paste a network programming interface that enables durable zero copy to non-volatile main memory, and it helps the application organize the persistent data structures. And we can also let the application to keep using TCP/IP in the kernel, and the application are also protected. And also the one important thing is the paste offers high performance network stack in general, even without the NVMM, which means if you write your application using paste, then your application is ready to support NVMM. So paste is actually under active development, and currently it is a branch of NetMap, but we are currently working on the merging this branch to NetMap master. So in the future, if you don't see anything in this URL, let's try with removing tree/paste. And also, if you have any questions or something, then just drop me email or just mention in the Twitter. Thank you very much, and I'm happy to take questions.
We have some time for questions. So are there any questions? Let me start off. So it looks like you have to sort of write entire packets directly into NVMM,
yeah.
right?
Yeah.
Applications might not be interested in all the packet headers and things like that. But how does that play with wear out characteristics of some of these devices? Because you'll be writing a lot more data maybe than what applications actually.
Because the kernel knows the application data offset, so the kernel writes to the throat like this is application data offset, and this length is also the content of the packet. So the application can only see the useful packet data, because kernel tells to the application in putting some metadata in some green slot.
Okay. There's a question here.
Hi. So I have two questions. The first one is, how does the pbuff implementation you have? So it's fixed size, and how does that one? How do you implement that thing?
So it's fixed size means it's a configuration time. So you can change it, but by default it's 2 kilobytes of data. But what is precisely what you mean?
So what's the difference between your implementation and the mbuff implementation in the DPDK?
Oh, and buff DB, yeah, it's similar, but we create buffers on the NVMM, not on DRAM. And our packet buffers are backed by a file, so that we can recover data after reboot.
Okay. So can you support multiple applications?
What?
Multiple applications at the same time?
What application?
Multiple applications.
Multiple applications.
Yeah. So far, we have to rely on some SRIOB or some multi-queue NICs.
Okay. Thanks.
Okay, I'll ask you another question as the speaker setting up, next speaker setting up. So in many situations, you'll have compression and encryption being performed on packets, right? On sort of on the fly.
Yeah.
How do you see that working with this particular setting?
Of course, so far that we can't do that, but you know that the modern NICs are starting to have some offloading of encryption or decryption. So if we rely on such a NIC, then we can receive some encrypted packet and some encrypted packet, some content, and having that NIC decrypted, and then application see the flat data, plain data. So this is actually the direction what we are thinking right now.
Okay, thank you. Let's thank the speaker again.